Hello everyone, my name is Gabriel Olguín, and today I will present a section of my doctoral thesis called Novel MORE Potentials to study the copper-carbon-hydrogen interactions in copper capped by graphene nanoparticles for biological applications. This research is supported by Dr. Hans Alzate Morales from the Center for Bioinformatics, Simulation and Modeling of the University of Talca in Chile. It is the center where I also belong. Dr. María Belén Camarada from the Functional Materials Laboratory of the Pontificia Universidad Católica de Chile, and Drs. Germán Soldano and Marcelo Mariscal, both from the Faculty of Chemical Science of the National University of Córdoba in Argentina. Copper nanoparticles have attracted attention due to their high thermal and electrical conductivity, high melting point temperature, and high reactivity. It has given them uses in catalysis, electronics, and diverse biological fields. However, their high reactivity favors oxidation, corrosion, and aggregation, leading them to lose their properties of interest. Copper capped by graphene nanoparticles have also attracted the medical and industrial sector, because graphene can serve as a shield to protect the copper nanoparticles from undesired phenomena. Additionally, it has biocide activity and can be functionalized for different purposes, improving the copper nanoparticles applications. Copper capped by graphene nanoparticles have been already synthesized and used, but their size distribution, and number of graphene layers covering the nanoparticles still remain as a challenge. Considering that, we try to study the behavior of this nanomaterial through molecular dynamics, using potentials reported in the literature. However, due to they were created to study the interactions between copper and biological molecules and not for carbon materials, the result not converged, and it was not possible to use them. For this reason, new MORSE potentials to reproduce the behavior of copper capped by graphene nanoparticles through molecular dynamic simulations are reported. The interactions parameters for copper with carbon and hydrogen were obtained from DFT planar wave cell consistent field simulations. It was applied in 194 configurations, consisting of a single flake in different orientations and curvatures, on in a portion of each phase of the copper nanoparticles. Then, single-point energy calculations were done, obtaining a good agreement between the quantum and classical simulations where the potentials were applied. In Quantum Espresso, the PBA generalized gradient approximation functionals for the exchange correlation terms was adopted, using the high throughput GBRB pseudopotentials. The best fitting was achieved when two different types of copper atoms were considered. Those with a low coordination, which means a coordination number lesser or equal to 8 in yellow, and those with a high coordination in orange, we have a coordination number between 9 and 12. Next, these MORSE potentials were used to evaluate the structural behavior and thermal conductivity kappa of copper capped by graphene nanoparticles when they are in an argon environment. In other words, a copper capped by graphene in argon nanofluid was studied. Nanofluids are colloidal suspension of nanoparticles in a base fluid. They are interesting because they have exceptional thermophysical properties, like a high thermal conductivity and low nanoparticles volume fraction. Also, they have been suggested as a good alternative in drug delivery due to their stability and because they allow the nanoparticles homogeneously disperse in a medium, which has not been observed in fluid with milli or macro-sized particles. Here, 10 models of nanofluids with nanoparticles from 1.5 to 6.1 nanometers were considered. 5 of these were uncapped copper nanoparticles, and the other 5 were covered by 14 graphene flakes. In the image, the argon is omitted to facilitate the visualization of the nanoparticles. Then, molecular dynamic simulations were done in lamps at 8 temperatures from 100 Kelvin to 800 Kelvin, repeating each simulation 6 times. The copper-copper, carbon-carbon, carbon-hydrogen, and copper-carbon-hydrogen with argon interactions were reproduced with embedded atom method, IREVO, and Lennard-Jones parameters already reported. The results indicate that copper capped by graphene nanoparticles are stable in an argon environment, and their structures remain similar at all temperatures. The copper capped by graphene nanofluids have an improved thermal conductivity compared to the copper nanofluids, being up to 20 times higher for the nanoparticle of 1.5 nanometers and up to 4 times for that of 6.1 nanometers. Other studies that we did suggest that the size, number of flakes, homogeneity of the graphene cover and its orientation to the copper surface don't affect the thermal conductivity of the copper K by graphene nanofluids. Also, the number of layers per flakes improve the thermal conductivity of the copper K by graphene nanofluids. In conclusion, the developed MORSE potentials are able to reproduce the structural behavior of the copper K by graphene nanoparticles and are useful to calculate the thermal conductivity of copper K by graphene in argon nanofluids. These results are in a good agreement with calculations carried out for copper nanoparticles in argon and graphene flakes in argon, and with the studies already reported for these materials separately. Thank you so much for your attention and your time. Have a nice day.